Thank you. So I'm quite excited to come to this event. There's so many lovely topics about different sorts of math. So what I will talk about is my projects with the Met Office when we're trying to deal with the space weather models. And one target is to use the deep learning technique in dealing with some of the satellite observation and numerical observation we have got. Oops, sorry. Can you see the next slide, or is it this first one, just to check?
I can see the outline now. Is that
great? So it's working properly. Okay, so well, it's already the end of the last two talks, so I'm trying to make things less stressful. So I'll try to put more stories instead of math in my talk. What I will introduce here is about the major project we're doing and the set of things we're targeting. So space weather, we saw it in the previous talks. Matthew has introduced the concept of space weather, but it is from the energy sector's point of view. Space weather have way more impacts if you talk to satellite engineers and even national grid, because when you have any of those extreme events happening, things like magnetic field, sorry, just move this, like magnetic field explosion or X radiation, fast speed particles, and various of other things happening, they're causing various troubles. And the space weather is not only traveling fast, it depends on the weather condition you wanted to target. So there are electromagnetic wave storms. This will be the speed of light. So if you observe it, it will target Earth within the next few minutes. But there are also way slower and heavy particles, which will come possibly a few days after you observe the occurrence. So the impacts of things can vary, depends on the different type of scale and different type of sectors you wanted to look at. And of course, the most important part is you have the engineers building up several different sites of things so they can avoid the thing when it happens. Another really important thing is we can observe it properly and forecast it correctly. So the thing we're working with is Met Office, where we use some of the NASA's model, and we're trying to improve some of their model. Okay, sorry, it was. Yeah. So when we're talking about space weather, there's one background condition we need to talk about, that's the solar wind. So there's keep having particles or other type of things blowing from the sun. You can consider them like a terrestrial wind, but it's just way faster. The average speed is around 400 kilometers per second. That's a really slow wind. And when you have extreme events happen, they can go up to 800 kilometers per second. These are already really gentle compared to all the extreme weathers, and they're happening every second around the Earth. So that's one bit of the thing we wanted to correct the current models, and we wanted to improve the model. Then we can use the data to predict more accurate extreme events. So this is the set of model we're using in Met Office and NASA. And as you can see there, but it's really, really complicated, but I will just quickly explain, because there are different sets of MHD or the solar physics conditions, and then you have different sets of MHD equations. On the surface, the most original data come from an observatory called Gong. So Gong will produce a lot of data. One important data we use is the magnetogram produced about the sun. So based on that, because the Earth is rotating around the sun, but you always have trouble. There's half of the sun's surface is away from Earth. So you always have half of year hidden behind in a way. So in that sort of case, especially that's the case with the polar region, because if you think about the tilted angle, and you always have part of it missing. So how do we do that? And then there is a model created by a set of top scientists called ADAPT, which using some transport model and data assimilation to correct the far side mistakes and trying to input more accurate data to the Gong image we have. But even so, with the input data, then you need to put it to, you will see here, WSA, three sets of WSA, and eventually our space weather or this solar wind comes to this annual model where you can simulate across the whole solar system. So those are the big MHD monsters, but in order to solve them or improve them within a fairly good amount of time, what we observe is the input values. As we mentioned, the ADAPT actually doing a fairly good job compared to the raw GONG images. And if we still wanted to improve it, that's where we want to target. So if we can improve ADAPT or know how ADAPT is working, then that can help our numerical model to be more accurate. So here we are thinking about to use machine learning models. The reason is, which I will explain slightly later, because we're targeting these 3D magnetic fields, which projected on the 2D image. Those are highly complicated physical phenomena. So in order to understand them and to modify them better, there's nothing better compared to a deep learning, because deep learning is in image reconstruction and recognition is doing far better than what human can do. So that is our main target. Of course, we wanted to improve the forecast result, but at the first stage of my first 2 years, we're trying to understand the images and combining them to make a better input value. So here we're using a deep learning tool and a bunch of numerical methods trying to improve this set of prediction models. And the set of model we're targeting is the data coming out from this model called WSA, which is using the GONG synaptic map, and you can also use the ensemble output of the ADAPT. So what is ADAPT? Well, I use Python to deal with the set of data, which I will just skip it. And most of the data can come from several different types of satellites. Some of them are Earth-based, and some of them you can even use other special orbits. So what is ADAPT? ADAPT is doing some sort of model on these GONG images, and then they push and correct certain things we couldn't observe. And they produce 12 ensemble outputs of the same moment after simulation. So why do I do that? And if you see the video on the side, clearly you can notice the pattern varies quite a lot. But it is also really funny because this is supposed to be the same simulation of the same moment. So that is the question. Which of these 12 for every single moment we got is the best choice? Then what we want to do is we wanted to understand which one's the best choice. Oh, excuse me, I forgot to introduce, this thing is called a Chronohole. So this is, you can imagine you have all the magnetic field lines and there's an open part, where is the open part is actually pushing out all these different type of particles and magnetic storms, this sort of thing. If they are big, you can have a CME, where is the coronal mass ejection, such and such. So they are always happening there, but they change based on the physics side or the property of the sun. And for the sun, they have a rough period around 9 to 12 years. So the major polarity will swap, and the sun surface have loads of different polarity on top of it. So they always change at the time. So modifying these changes of coronal holes matters a lot to our background solar wind. So as you can see, it sounds like easy, it's just a hole, isn't it? Well, the thing is, if you see on the top, this is a normal proper satellite images, but can you really see the coronal hole? We can't, it's not something really obvious. So even for professional forecasters, they used to do this segmentation by hand. And here we use one type of algorithm, which was also produced by one of the PhD, but have graduated, is with a Met Office. So it's called Chimera. So I'm using the Chimera, assuming it's the ground truth, and trying to compare it to our WSA output or the ADAPT output, the 12 ensemble. But if you pay attention, you notice there's a problem. They're not in the same coordinates. So how do you compare? So the first set of my project is to deal with this messy projection problem. You need to think about that. The sun is not solid, so there's no fixed reference on the point. So you need to refer to the location of the sun's coordinates and the Earth coordinates, and whatever time when they were merging at a point, and then you can use that as an initial location. So after a set of complicated calculation, I've shown two brief images here. This is the ensemble output. You project it back to a sphere where I squash it back to a circle. And this is the chimera output of the Chronohole, and I project it back to a WSA output. So this is just an illustration about the algorithm I did for part of the results, but I won't go into too much detail about it. It includes a lot of complicated data processing and also related to the satellite location orbital projection thing. So if you're curious about Chimera, this is what we got for a whole 27 days. So in our period, it's not entirely a whole month because the Earth is moving, the sun is moving. Every time when the same point meet, there's roughly around 27-day point two. And of course, this the solar surface rotating at different speeds at different latitude, or if you say that. So because most of the chronoholes is in the region and their rotation speed is 27 days, that's why we take 27 days as a period. So as you can see, this 27 day is the rotating of the sun. What I did on the other side, well, the picture, the color here, just to make the picture beautiful, is not what we feed into the model actually. So you project this one and make a synoptic map of the solar globe like that. And when we done these complicated projection parts, we can continue with our neural network models. So on the satellite output chimera, or maybe it can be one snapshot like that, or it can be this synaptic map like this. And then we wanted to compare to our original ensemble outputs. Calculation, we're trying to see the reconstruction result. Of course, there's one thing need to comment out on the loss function. We're only comparing to the size that is available to the snapshot. Because if you pay attention on the corner, well, I think I'll show this one. So if I'm comparing to the snapshot of the chimera, this is the projected chimera. And if you should be able to notice there's black side because that is the backside of the sun. And of course, we're not comparing to all of it. So we have a mask covering this shape. And so we're only learning within this region. Of course, the region will change, but that was based on our projection data. So we couldn't do a simple mask layer as most of the problem could have do that. And so this is just a simple toy output. Of course, if you say, how do we understand it? This is not really for understanding. It's just for seeing that our network or the toy model actually works. So the conclusion so far is we have the major part of our projects, actually the data pre-processing and the image register, which I briefly mentioned. You have to deal with different orbital data and you need to project them like to like. They need to be on the same coordinates. They need to match to the same time, such and such. And we consider various different types of synaptic map construction. If you remember, that was the global map of the magnetic field. There are various different type of things happening in this synaptic map reconstruction because in our project, we need to eventually combine the data from different satellites. And of course, the satellites not only Earth-based or close to Earth, they can be located in other places. For example, the famous probe that is flying into the solar atmosphere, because our model can do this projection automatically. So the location or the orbit is no longer a problem, but I didn't present that thing here because it's way too technical. And another part is the main work of our current result is the CNN neural network model of CNN to do the reconstruction. We have done the toy model. So what we are trying to changing now is to use adaptive CNN on the sphere instead of on a latitude and longitude mesh. Because most of people here doing a numerical model, so you should know that they will transform, causing lots of troubles in this sort of projection. So we're aware of that. So we're trying to change the topology or whatever you wanted to call it, and we wanted to use a different type of CNN. And the loss function is apparently not really accurate, and we have two different ways to approach it. First, we want to try use the signed distance function, or another way we can use the Wasserstein distance measurement to compare how the two maps being mapped. So there will be a bit of optimal transport used in our model. For the activation function, we have a few, we have talked to a few people in the theoretical research, and they pointed out a few exciting results. They've got things like rational functions. So we're planning to use rational functions to do the reconstruction. Of course, the deep learning currently is definitely a shallow structure, which is nothing appropriate. We definitely need to go for a good deep CN layer, or maybe we're even possibly we wanted to combine with other structures, but that would depend on the research. So we haven't given too much thought about the deep learning structures yet. And the ensemble rank matrix. So MetOffice wants this a single ranking matrix, but our model is planning to give them not only the matrix, but also the reconstructed, a better result to feed into the data. So I think that will be it. I don't want it to crush you with too many technical details, but feel free to ask if you're interested. So I think that's all my talk. Thank you.
Thank you very much, Tina. That was great. So you've already got some questions.
Oh, sorry, I didn't see that.
Oh no, it's quite all right. We've got plenty of time. So Matt, I know you had two. Did you want to unmute and ask, or I can read them out? It's up to you.
Yeah, that would be great. I mean, we got time, so why don't they ask if they want? Because I can't really see them in this full screen part.
Yeah, I have unmuted. Hopefully you can hear me. I don't have my headphones on anymore. So
yeah, I can hear you, yeah.
Okay, good. Yeah, thank you for the talk. It's good to hear some more space weather related things going on. So thank you. And yeah, your work with the MetOffice sounds really exciting, and well done for doing this work.
Thanks.
Yeah, I guess my first question was like really general, like, 'cause you were talking at the towards the start about the ensemble of models that were being used, and it just got me thinking about the upcoming Lagrange mission that is being run by the European Space Agency.
Yeah.
And I'm sure you've heard about this mission, but it's they're planning to put a space weather observation like
L3, yeah,
system at L5, I think it is. So it's
was it L5 or L?
Yeah,
L5, the one after Earth. Yeah, it is. There's a collaboration with MetOffice. Yeah.
Yeah, so it'll allow observation of a bit more of the far side of the sun before it rotates around to,
so we have
the UK.
That can allow us with 3 months ahead of data.
Yeah. So do you how much do you think this will improve this sort of forecasting model and systems? Do you think there'll be a big improvement? Or do you think
that's a really important thing, actually? That's why there's one thing I didn't really mention too much about the synaptic map, because then it evolves about the physics related. So the trouble is, if you see this synaptic map, even though it's a whole cycle, you notice there are a lot of things missing, isn't it? Because that's the part of the data we couldn't get if it's only satellites from close to Earth or Earth-based observatories. We just simply couldn't get them. So there's an L3 point or L5. There are two positions that could give really good results. So if you have L3, then we can say that nearly a third of these images will be completed, and that'll be way more valuable to cause a lot less trouble. And if potentially possible, we can get L3 satellites though that'll be in the far future, because that's right, you have to send the data across the sun, which will cause a bit trouble, or maybe you need the L5 to transmit the information or something, then you will have entirely no error image. That will be perfect for our input. Because why we're so certain is the input value causing the trouble. That's related to my MSc project with the Met Office. That one I did a verification modeling for the whole set of models I explained here. So what we observe is once you have different input value, if you increase the accuracy on the input, the different sets of MHD models can give a fairly good simulation. So yeah, I'm waiting for that one, but I'm actually a bit worried about the COVID because it's supposed to coming out next year, but I don't know whether I can have it next year actually. But Parker's data might be useful in a way.
Yeah, no, that's exciting, and yeah, I hadn't even considered a spacecraft at L3, but yeah, that would give an amazing extra view of the sun. This is probably jargon for other people, so just as a bit of an explanation, that the L points, they stand for Lagrange points, and they're all the different points in this solar system where the gravitational fields from the sun and the Earth cancel out. So it's like a really useful place to put a satellite because you don't need to use any power to stay there. You can just plonk your satellite in this point and it will just stay there without any power. And there's there's one that's like ahead of the Earth, which is where
it's something like here, if you
going.
put a triangle there, somewhere there, and there's another L5 is here, and L1 is there, L2 is behind Earth, and L3 is right across to Earth. Yeah,
exactly. So if you can put a satellite at any of those points, like L3 that's across the sun, or L5, then you basically get a different view of the sun than you do from Earth, which is really useful when you're trying to like get around this observation bias that we have from the sun, from the Earth, where we can only see one side of the sun. And if I may, I'm going to ask another question. I was interested. I'm not very good with machine learning, but I'm trying to get better with it. So and I've come across this idea of transfer learning quite a lot, which seems to be very popular and can create some very powerful results without the need for like really intense training, because a lot of it's already been done. So I was wondering whether you think transfer learning will be useful for your work here, or whether it's too unique a data set that
I actually have no idea. I haven't think about it because we're mainly targeting the physics based. So I didn't fully explain what I was planning to do. So this is one of the major part of the project. So what we're doing is we want to use this one as the first thing is to select adapt output, as you see here, before feeding it into other layers of WSA and ANLIO. And another bit I need to do is actually, we wanted to update something we observed is actually a mistake in the WSA reconstruction model. So the guy from NASA who developed this model, he also pointed out because the data processing itself is really complicated, but currently our model, like the one I developed, is capable of dealing with that automatically now. So what we wanted to do is we want to use our current model, if successful, as an auto selection process for WSA. And on top of WSA, we wanted to fix a few things and then do a data assimilation to update WSA as that. So I don't really know how we will use the transfer type of learning. That will require a lot of more investigation, because CNN is not that black box. You can observe what is happening after every layer. So yeah, but it could be a good idea. I can possibly have a look.
Okay, thank you very much for in-depth questions and answers. That's great.